the next talk will be held on Zoom. So it will be given by Jaiswal, so from the University of Bologna. So are you here?
Yes, I'm present.
Yeah.
Yeah, but
okay. So
so let me see if I can
share your screen.
Yes, I'll start sharing my screen. Let me just. Okay. So is my screen visible?
Yes.
And is the presentation visible in the normal mode, or is it more like not the normal mode?
No, it's not in full screen.
So I should make a full screen. So
okay, as you can see,
like this.
It will be about non-adiabatic dynamics of solvated tryptophan.
So now is it visible in the full screen way?
Yes,
yeah. Okay, so I will be talking about the study I did about this non-adiabatic behavior in solvated tryptophan. So it's not a very developer kind of presentation, but more like a consumer kind of presentation. But I hope it's still interesting for this developer conference. So it's a kind of a photophysical journey or photophysical investigation into the behavior, ultrafast behavior of this solvated system, which needed the right CASPT2 method to really understand what was happening. So just to give a small introduction, why we study this molecule, because this tryptophan is present in all proteins. It's a very strong fluorescent molecule, a sensitive probe of the protein structure and environment, and so it's crucial to understand how it behaves at an ultra-fast level. And if we look at the history of the electronic structure of such systems, this was started by Plath in 1949, where he postulated that you can understand these systems by electron in a ring, and with this approximation he solved the one electronic structure and he assigned a nomenclature, and he found these two low-lying excited states called LA and LB, which are present in these ring-like systems, and these are characterized by quite different polarization diagrams or distribution of charges. And if you see like these LA and LB states, which are kind of present in such kind of ring systems, are quite they have quite different behavior. You have this LA state, which is much more sensitive to perturbation, while this LB state is quite less sensitive to perturbation. In the figure below, the perturbation is just the number of rings that you see. These are all from the same paper in the 1950s. And so with this kind of knowledge, people started studying these kind of ring systems, and started to study their absorption bands in various different environments. And of course, if you study the absorption band of tryptophan or indole or the chromophore indole in various different solvents, you see that, of course, the LA state is quite sensitive to perturbation. So based on the solvent polarity, you see shifts in LA band, and the LB band is quite less sensitive to perturbations. This is all like ancient knowledge. I'm trying to summarize what is known about the behavior or the excited state behavior of the system. And of course, LA state has 10 times more oscillator strength or much more transition dipole moment from the ground state. So it's much more brighter than the LB state. And of course, if you try to resolve the bands of LA and LB, they are very, very overlapped. So it's quite difficult to resolve them. So of course, any ultra-fast behavior will involve the interplay between both of these excited states. This is a kind of summary of what was known about, or what is expected to be known about the ultra-fast behavior of tryptophan or indoles in vacuum. You have the LB state, which is the most stable one, and LA state is above it. But if you go to a polar solvent, due to the highly polar nature of the LA state, it's expected that it will be stabilized, and so the LA state will shift below the LB state. And of course, when the solvent will respond dynamically to it and it will relax, the gap between them will increase. So we can study this dynamical behavior with transient spectra. I think everyone knows what is the transient spectra. You populate a state and then you collect both absorption and stimulated emissions, which are fingerprints of what populations are being transiently created. This is just a figure for people to see how you do a transient spectra and what spectral fingerprints you collect. Okay, so based on this transient spectra, people studied the ultrafast dynamics of tryptophan, and they assigned any internal conversion from LB to LA. I mean, this was a very, very ultra-fast sub 50 femtosecond internal conversion from LB to LA, because it's thought that LA is more polar, so it will be stabilized. So any internal conversion is just this. And then you have these two longer time constants, which are just attributed to the solvent response, because from the seminal paper of Maroncelli, from molecular dynamics, solvent response has these two kind of time constants. One is a ballistic response, and one is a more slower picosecond timescale response. So also, if you look at even more newer papers, any ultra-fast dynamics is just LB to LA, and you just record some solvent relaxation, nothing interesting in transient spectra. If you look at even the newest paper from 2012, they still postulate the same thing. You have an LB to LA internal conversion within sub 50 femtosecond, and after that, you have just these two time scales of solvent relaxation. So, okay, this is what is the summary of what is known about tryptophan. It has these two close-lying singlet states, LA and LB. LA is quite sensitive to environment changes. In a polar solvent, LA is the emitting state. And any ultra-fast dynamics is just a sub 50 femtosecond, very quick LB to LA internal conversion, which is followed by solvent relaxation of the LA state. This is a figure to say the same thing. In vapor, you have this energetic order, and in a polar solvent, LA is more stabilized. So you have this fast sub 50 femtosecond internal conversion and a solvent relaxation. So it feels like everything is well known about tryptophan. So why are you studying it? But the thing is that in the past 10 years, huge amount of development has taken place in both experiment and theoretical side. So we can investigate and we can see if we can improve this picture, or we can see what we see with this newer, much higher temporal resolution and much more accurate electronic structure methods. So this is a simple QMMM setup that we use to make computations. You make a water sphere, you describe your chromophore quantum mechanically, and you describe the effect of the solvent by electrostatic embedding, which in Molcast is just adding an X field section. And we use Cobram to kind of do a subtractive QMMM so that we have the full QMMM energy of the whole system at a CASPT2 or whatever electronic structure level. And we can compute the absorption bands. This is well known. And here I'm showing you the absorption bands. But most interesting thing, not the most interesting thing, the most relevant thing is the two pump pulses that the experimentalists use to selectively excite the two regions, so that we can say that, okay, we are populating LA or LB, and to kind of follow the dynamics. And these are the orbitals which are involved in the transitions of LA and LB. I think the most relevant picture is the one below, where you can clearly see that LA is more like an internal charge transfer from the 5-membered ring to the 6-membered ring. That's why it's so polar, and that's why it's so sensitive to environmental perturbations. Okay, so with this QMMM setup, with this highly accurate CASPT2 method, we optimize the structures. And we characterize these critical geometries of the various excited state minima. And what we obtained was that the LB is the global minimum. But just to kind of clarify, these optimizations are taking place in a solvent environment which is relaxed to the ground state, because when you do a geometrical optimization, only the bond lengths of tryptophan are changing. So the situation in front of you in the present slide is what is at the time of the pump interaction, let's say, when the solvent is still configured according to the ground state. And at this time, we see the LB is the global minimum. So this means that at early times, we would rather see an internal conversion from LA to LB, which is quite different. And the fact is, if we compare now with the experimental transient spectra, with the latest ones that we have, and we compare that with highly accurate CASPT2 computations from the LA and LB state, we see this is indeed true. At early times, at 50 femtosecond, we are collecting transient fingerprints from the LB state. And only a long time, from 50 femtosecond to 1 picosecond, we have this conversion from the LB state to the LA state. So we don't have a sub 50 femtosecond LB to LA, but rather we have a sub 50 femtosecond LA to LB, which is quite opposite to what is commonly written in literature. So how does the ultra-fast sub 50 femtosecond population to LB occur? Well, we know that LA is much more brighter, so we populate the LA after pump, and ultra-fast population to LB will, of course, involve a conical intersection. So we try to make a branching space. So first, I made a branching space at the CASPT2 level. Here you see your two adiabatic surfaces, and on the color map below, I'll show you the transition dipole moment from the ground state. So we can clearly demarcate regions of LA and LB on the lower adiabatic surface. So of course, at maybe this is obvious for theoretical people that of course at CASPT2 single state CASPT2 level you cannot resolve the branching space. Rather, I just see a conical intersection seam. So I see a diabatic part to the LA minimum, but of course, single state CASPT2 cannot describe the branching space. But still, I see the LB region is more stable than the LA region on the lower adiabatic surface. Then I do the multi-state CASPT2 because multi-state versions are supposed to describe the branching space better because the states are kind of orthogonalized at the PT2 level. And of course, we see the conical intersection, but the behavior looks quite dramatically different because rather than two minima on the lower adiabatic surface, I see a continuous valley connecting these two diabatic states. And this doesn't even look coherent with what experimentally we see. If I try to do it XMS CASPT2 level, I see the conical intersection at a slightly different nuclear region, but it's there. But here I see an ultrafast part to the LA region, and the LB region, which is in blue, is quite destabilized. So there is no way that you would populate LB. I mean, after pumping, the population will just collect in the LA region. So all of this looks incoherent with what we were observing experimentally. So I thought, okay, we can improve CASPT2 by, okay, so this is just a summary of what we saw with the standard active space, so with all the valence orbitals in the active space, and none of them are describing the ultrafast population sub 50 femtosecond to the LB state. But okay, the single state CASPT2 obtains the expected adiabatic energetic order that the LB region is more stable than the LA region, but we cannot describe a branching space at the single state level. So to improve, I expanded the active space to collect more correlation. So I add like 4 orbitals in RAS3. I mean, after I add the 4 orbitals, these 4 orbitals don't have very huge population. So I'm preserving the original state, but I'm just kind of describing more correlation statically. So now at this expanded active space, which I refer as augmented XMS CASPT2, I have the expected behavior that the LB region is more stable than the LA region on the lower adiabatic surface. The conical intersection we have, and we have the LB region more stable. It's an expected behavior. Here I compare this augmented XMS CASPT2 with the original XMS CASPT2 with the original active space, and you see how the energetic order in the lower adiabatic surface is kind of reversed with one in both of them. And here I compare the augmented XMS CASPT2 with the standard rotated RMS PT2, which is the new thing in open MolCAS, which is I think you just do the XMS rotation, but then you do a simple multi-state on the XMS rotated states. And here you see actually the RMS PT2 with the normal active space gives a branching plane, which is very, very similar to this augmented XMS PT2. And because this augmented XMS PT2 has a bigger active space, I can, in a kind of safe way, take this as the reference. So here RMS PT2 is actually giving the, let's say, the more correct one, or it agrees with the reference better. So here I show you again the lowest adiabatic surfaces. So you can really appreciate how they look different, the single state, multi-state XMS and the RMS and the augmented XMS. And you see really how the stability of the LB region or the LA region on the lower adiabatic surface. And you see really how RMS and XMS really agree with each other. The multi-state is completely crazy. I don't know what it is predicting. The XMS predicts a reverse order. The single state is not so bad. It predicts the same energetic ordering. It just does not describe the branching space. So we have a conical intersection seam, but the adiabatic order is quite nice at the single state level. Okay, so with this correct description of the branching space, we have now a correct explanation of the ultrafast behavior. So you populate the Frank-Condon region, you ballistically reach the conical intersection, and then from there you can go to the LB region, which is more stable. So at early times, we'll have a propensity for the population to be collected in the LB region. And that's why we see transient fingerprints at 50 femtoseconds from the LB region. So, I mean, for the developer stuff, this is the conclusion that we needed to use the appropriate method to describe the photophysics. And we are confident that the method that we have chosen, the RMS method, is good because it agrees with the augmented XMS that we can take as a reference because it has a bigger active space. So we can just, I will just continue a bit to kind of finish the photophysical story also. So this is the summary of the initial response. We have an ultra-fast on adiabatic conical intersection assisted population to the LB. And the initial sub 50 femtosecond internal conversion is not LB to LA, but LA to LB. And what is the reason for this? Because at these times, at these early times, when the solvent is still oriented to the ground state density, it is LB, which is the adiabatically lowest state, contrary to the LA. And this manifests in experiment as a population residing in LB at around 50 femtoseconds. So now, how will the environment respond to this? So the wave path, so after it goes from the conical intersection and goes to the lower adiabatic surface, it has a lot of energy. The wave packet has a lot of energy. So the wave packet can coherently explore the regions of LA and LB on the lower surface through active molecular vibrations. And the solvent will respond to the electronic density of these states. And so to study this dynamical response, we can model this. How do we model this? In a very simple way. So excitation to the LA or LB results in a redistribution of electronic density. So it leads to a redistribution of charges on the solute. So we can just fit the charges from CASPT2 at the nuclei, and we just run a simple classical molecular dynamics. So it's just we put the new charges of LA or LB, and we just run simple molecular dynamics to kind of model the time-dependent behavior. And to understand the solvent response, we track the adiabatic gap between LA and LB, between the excited state minima. And here you see, if the solvent, if I do this the dynamics around the LB state, the energetic order is preserved. That LB is LB is always more stable. But if I do the dynamics around the LA state, a reversal of order occurs, and LA state gets dramatically more stable, and the energetic order is reversed. And just to clarify, these trajectories are not just one trajectory; they are ensemble average over 100 trajectories. So what you're looking is really an ensemble average, not just one molecular dynamics. Okay, and if you try to understand why this is happening, it's happening because of the electrostatic response, because the LA state is much more polar. It has an internal charge transfer from the 5-member ring to the 6-member ring. So of course, a polar solvent will really respond to it very strongly, and you have a strong electrostatic relaxation along time, which leads to the stabilization and the energy and the inversion of the energetic order. And what is the consequence of this solvent response? So we can compute the same branching space at a solvent configuration now at 1 picosecond, and you see there's a dramatic change in the topology of the branching space, and the LA region gets completely more stable. There is no minima in the LB region, and so the population can just tumble down from the LB to the LA, and this explains how the population which was in the LB region but was able to coherently explore the LA regions through molecular vibrations and activate the solvent response can lead to the population tumbling down and collecting in the LA region along time. And of course, what are the consequences of the solvent response on the transient spectra? We want to see if it is affecting. I computed the transient spectra. Again, these are over 100 snapshots for every time slice. So this is really an ensemble average. And you see, it doesn't lead to any great shifts in the photoabsorption band. You just have kind of slight intensity changes. So this means that these shifts that we saw in experimental transient spectra are really encoding a population transfer from LB to LA and not just solvent relaxation. So we are really confident in how we're interpreting the photophysical behavior. And so of course, so the vibronic coherences trigger the solvent response from the LA to the LA times. So of course, are there fingerprints of these coherences in the experimental spectra? Yes, there are. So if you kind of remove the spectral dynamics, you have this very nice oscillation map. And if you track the point where the phase jump happens, you see that the phase jump is really shifting in time. And this phase jump encodes at which point the emission is happening. And we see this emission is really shifting in time. And this means that even though the transient spectra has a population in LB, it still has in these oscillations, in this shifting phase jump, a fingerprint of the LA state at the early times, because we fit the LA emission and the LB emission from the molecular dynamics, and we compare with the phase jump position, and we see it really agrees. So we have a fingerprint of a presence of this LA state at early times, even in the experiments. So this is the conclusion of the photophysics of tryptophan that I studied with CASPT2, and that needed the right CASPT2 method to understand it more clearly. So you have a substance initially when the solvent is relaxed to the ground state, you have a population to the LB, but because the lower surface is flat and the molecular vibrations are active, the molecule can explore both LB and LA region, and this triggers the solvent response, and this results in the population going from LB to LA with a certain time scale of, let's say, 200 femtoseconds. And so these are the conclusions that I have said. A sub 50 femtosecond CI event is LA to LB. The transfer to LA is an adiabatic transfer. It's not so the transfer that happens along time, along the molecular dynamics, that does not involve any conical intersection, but it's just an adiabatic transfer. And we have a vibronic coherence between LA and LB, through which the solvent response is triggered. And these are the conclusions from the instrument, that because we had access to this very high temporal resolution, sub 20 femtosecond transient spectral recording instrument, we were really able to resolve these finely nuanced details in the photophysics of the system. So I just thank all the people without whose help this study could not have been possible, the team in Bologna and the team at Milan, with whose help this whole study was done. Thank you all.
Yeah, thank you very much.
And
we can afford one very quick question. Seems not to be the case, so thank you very much again.
Okay. So if there is no question, I have like one humble, I mean, my whole aim of presenting this at a developer conference was just to have a humble request, because as you see, my study requires a lot of CASPT2 computations over hundreds of configurations in which the solute geometry is fixed, but only the X field changes. And for this, I have to feed the CASPT2 like hundreds or thousands of times. And this is really time consuming, but I feel this could be smart. I don't know. I think there could be a way where if I have one computation in one X field and I just want to freeze the wave function and I just want to change the X field and I want to do a new CASPT2 or an XMS CASPT2, if there would be a faster way to do it rather than repeating the whole CASPT2, it would really help me, because now I'm planning to move to much more bigger systems. Like this is a dimer system here, and here you see with just a frozen solute, but with decorrelated solvent snapshots, you have this charge transfer energy in red, which completely has a huge variance in energy. And in these much bigger dimer systems, I cannot just do CASPT2 on one structure and have some intuition. I really have to do CASPT2 on a whole decorrelated solvent or a flexible environment. So I was thinking, if there is a way, if this could be done faster, it would really help me. Thank you all.
Yeah, thank you.